Okay, in this video, what I want to do is I want to solve the second problem on the test. This is the description of the second problem. Basically, we have a turbine that's being fed by a flow of fluid. And in this particular case, we assume that the two stages of the turbine are isentropic. And then there is a certain amount of fluid that is pulled out of the turbine, extracted at some pressure associated with state 2, goes over to a feed water heater. The rest of the fluid goes through the turbine and goes down to the low pressure of the condenser, and then it condenses down to the saturated liquid condition. It then gets pumped up to the pressure of state 2, mixes with the fluid at state 2, combining together to be the full flow rate, then going into the second pump, and the second pump then brings it back up to the pressure associated with the incoming of the turbine or the outgoing of the boiler. So in this particular case, what is given is that this temperature, this open feed water temperature, was given as 150 degrees Celsius. Okay, so now the modification that's necessary for this particular problem is to replace this open feed water heater with a closed feed water heater. And so what's going to happen then is that the extracted steam is going to come out and it's going to go into the closed feed water heater. It's going to condense to the saturated liquid condition, and then it's going to be trapped back to the condenser. And it's then going to join back with the rest of the fluid. And then this pump here, pump 1, is then going to pump the fluid up to the pressure 1 instead of the other intermediate pressure, and then that is going to come out. It's going to come out at state 8, and that state 8 is going to have this temperature of 150, and that state 8 then is going to go through the boiler, and it's going to then continue in the process. And so what's going to happen is that this pump is going to be eliminated. State 6 is going to be the condensed condition, and state 7 is going to be after an expansion trap valve, and 7 is going to feed into the condenser. And so we're going to keep the turbine. The turbine device will stay the same. The condenser will have to have another inlet. The pump will raise the pressure all the way up to pressure 1. The closed feed water heater will have 2 coming in and 6 going out, with 5 going in and 8 coming out. And so it's going to be a non-mixing closed feed water heater. So with that in mind, I'm going to put this away. I'm then going to bring up my I have my input for the original problem. This was available to you. I'm going to select the states as well as the devices, and I'm going to copy that. Whoops. Let's see here. I'm going to copy that, and I'm going to put that away, and now I'm going to go into the software. Okay, so I've launched the software. The test app is going to be the vapor power system, phase change fluid, and we go into the HTML5. And so now what I'm going to do is I'm going to go into the I/O panel as before, and we're going to paste in that information and load it. And so upon bringing all of that information in, I then have all the state panels identified, along with the pressure and the temperature. This is what's coming out of the boiler, going into the turbine. This is the extraction point of the turbine at 800 kPa, isentropic. State 3 then is the final point coming out of the turbine, which is at 8 kPa, again isentropic. This is going into the condenser. State 4 is coming out of the condenser as a saturated liquid at that pressure. State 5 is the output of the pump. The first pump is bringing up the fluid just to P2, which is the pressure of the open feed water heater. And then state 6 is the output of the open feed water heater, which is at 150 and at that pressure. And then finally we go into the second pump, which is isentropic, and we bring the fluid all the way up to the pressure, the final pressure, and then that completes all of the states. If we look at the device panels, we have the device panel associated with the turbine. We have one input and two outputs. We have then our second device is the open feed water heater, which had two streams coming in, mixing and forming a stream 6. We then had 3 to 4, which was the condenser. We then had device 4, which was the first pump going up to the intermediate pressure, and then we have the second pump going up to the full pressure, and then to top it off, we then have the boiler. And the boiler goes from 7 to 8. So we've got to now make some changes. Well, in this particular case, once we did a supercalculate, what happens is the supercalculate then solves all of the device panel equations, and one can then see at state 2 that the m dot then is calculated. Now again, we put in an m dot equal to 20 kilograms per second as prescribed in the problem. State 2 is the extracted amount of mass. Okay. Now, when we redo this problem, we are going to have to solve for a new m dot. So first thing I'm going to do is I'm going to just turn that off for right now. Okay, now state 1 stays the same. We have the same input. State 2 stays the same. It's an isentropic expansion to the extraction point. State 3 is the isentropic expansion to the condenser input. State 4 is the output of the condenser at the pressure of the condenser, so that will stay the same. It's got a quality of 0. State 5 now is one that we have to relook at, because now state 5 is going to come out at pressure 1. And so it's the only pump in the system, and it is going to be moving the fluid from 4 to 5 through the closed feed water heater and over to the boiler. So we have to make this change in the pressure. State 6 now is going to be, that's going to be the condensate that's in the closed feed water heater. And we know that that condensate is at the pressure of the extraction point. It's not at that temperature, but rather at a quality of 0. So it's the one stream comes in and it condenses, and now it's going to be pulled back out. And it stays separate from the fluid going through from 5 to the output of the closed feed water heater. And so state 7 now, instead of going to the boiler, state 7 is going to be trapped back to the condenser. And so this is going to have a pressure that corresponds to the condenser pressure. And what we know about this particular state is that it's not isentropic, but rather the enthalpy remains constant through that trap. And so now we have that trap that's trapping the condensate going back to the condenser. Now we have to add a final state 8, and the final state 8 is what's coming out of the closed feed water heater going over to the boiler. And we know that it's already been pumped up to pressure 1, and we know from the problem statement that its temperature is 150. And so it's gone through the pump. The pump is allowing all of the fluid to go through. The M dot for this particular fluid, is the full M dot, which is M dot 1. It's been raised up to 150, and that 150 is due to the fact that it's gone through the closed feed water heater and taken heat from the extracted fluid. And so we have this state 8 that we now need to work with. Before we go to the device panels, let's just make sure that all the M dots are right. Okay, M dot 7, 7 was the trap back fluid. Now, M dot 7 is really at M dot 2 because that was the amount of mass that went through the closed feed water heater that was trapped back to the condenser. Likewise, state 6 is also M dot 2. And so those had to be changed also. And that M dot 2 will be calculated once we set up all of our device panels. Let's look at M dot 5, or state 5. State 5 is going to be at the full M dot. It's going to be at M dot 1 because it's all been combined in the condenser, goes through the pump. And so our state 4 then, which is coming out of the condenser, it's also at M dot 1, okay? Because it's come out of the condenser and it's the two streams that have come together. State 3 is M dot 1 minus M dot 2. We know that that's the case there. Let's make sure that's M dot 2, yes. And then state 2 is the unknown M dot, which we're going to leave blank, and it's going to calculate. And then state 1 is the M dot equal to 20. So we have all of our states ready. And now we go to our device panel. So let's go back to the beginning. This is our turbine, and the turbine is still bringing in state 1, coming out at state 2, the extracted steam, and then the steam going to the condenser. Our device 2 now, used to be our open feed water heater. Now we need to change this to our closed feed water heater. And so we have to change it to a multi-non-mixing. And now with a multi-non-mixing, we come in out of the pump at 5. We then go through the device and come out at state 8. Okay, that was the feed water going through the closed feed water heater. It was pumped, all of it is being pumped up to the pressure 1, and it comes out at state 8, which we say we know what the temperature is. The other fluid then is our state 2 that comes out as state 6. That was our condensed state. And so we have part of the fluid going through there, giving up its heat, the other full amount of fluid going through, picking up heat. And so this device is no heat transfer as well as no work. And so that then is going to be solved when we supercalculate, and it will calculate then the unknown, which is M dot 2. If we look now at our third device, the third device is previously the condenser. Now the condenser is a multi-mixing. It's not a single flow in, single flow out. It's a multi-flow mixing. And so what's coming in is 3, and also what's coming in is state 7. Recall that got trapped back from the closed feed water heater. And what comes out then is our new state 4, which is at the same pressure, but it's the combined entire fluid. And we know the condenser has no work, and so no work means the W is equal to 0, and so this then will calculate the heat transfer that needs to occur. Okay, device 4 now is our pump, our only pump that we have, and that's between 4 and 5. No heat transfer, and so this one is still the same. It's just that 5 pumped all the way up to the highest pressure instead of the intermediate pressure. And then we go to device 5, and device 5 was the old was the old second pump. And so we can go ahead on this one here, and we can use 6 to 7 as the trap. And what we know about the trap is not only is the heat transfer equal to 0, but also the work is too. So that in essence is saying that the enthalpy doesn't change. And so we really don't need that particular device. However, it will calculate how much irreversibility does occur in it if we had a second law problem. And then we go to our last device, which previously was the boiler. But the boiler now is 8 to 1 and no work and all heat transfer. And so we've now established, the new devices. We have the turbine, we have the open feed water heater, we have the condenser, we have the single pump, we have the expansion valve or the trap, and we have the boiler. And so everything now is all done. We have all of our states, we have our devices. All we really need to do is do a supercalculate. And so upon supercalculating, then we can go back to our state panel and we see here's our state 1, here's our state 2. Now we have a different flow rate. And so it is 4.48 is what was extracted. Why more? It needs to be more because we're bringing the full fluid up to the 150 instead of just part of the fluid. Okay. And then we have state 3, and we have state 4, and we have state 5, and we have state 6. Again, state 6 is that same M dot, and state 7 is the trap-backed M dot, and state 8 then is the full amount. So we have all of our states and all of our device panels. Let's just check out the device panels. We go to the work, we go to the turbine, and we see that there's a certain amount of work being generated there. It happens to be 22.24 megawatts. We go to our condenser, and we see, excuse me, this is our closed feed water heater. And of course, it's going to have no work and no heat transfer, but a little bit of irreversibility associated with the two fluids. And then we have our device 3, and device 3 is now the condenser. And the condenser has a certain amount of megawatts of heat released or taken out of the system. We have then our pump. Our pump then has a small amount of work, put it into megawatts. It's a very fractional amount of pump work. We then have 5, which is our trap, which has no heat transfer, no work. And again, a little bit of irreversibility because it's an irreversible device. And then we have our device 6, which is our final boiler. And our final boiler has 54.1 megawatts of heat coming in. If we then go to our cycle panel, we then can start to answer the questions. The question is, what's the first and second law efficiency? And the first law efficiency is given here as eta thermal, and it is 40.7%, and it just equals the net work divided by the heat transfer in. And then the second law efficiency is also given in here, and it's 51.1. That is the second law efficiency. Now, the last piece of information that you're asked for is to calculate the second law efficiency of the closed feed water heater. Now, in order to do that, I'm going to go to the I/O panel, and I'm going to generate some numbers. And so what I'm going to do is, I know that the second law of that closed feed water heater is how much of the extracted steam, how much exergy of the extracted steam goes into the feed water. And so I'm going to say the N value, the exergy N is going to be equal to my M.4, M.2, which is the extracted mass flow rate. And then I know that it's coming in with a psi 2, and it's going out with a psi 6. Okay, 2 came in and 6 came out as the condensate. And so this is what the extracted steam lost in terms of exergy. It actually was, when you take the m dot times this psi function, it ends up being equal to 3006. Okay, and that would be in kilowatts. Okay, and so likewise, we can now say how much was actually picked up. You know, how much did we get out of that? And in that particular case, it was m dot 1, which is the full amount of fluid. And what happened there is that it came in at a low value, which is psi 5, and it went up to a higher value, which was psi 8. And so it's going to be psi 8 minus psi 5. 5 is coming out of the pump, going through that closed heat exchanger, and we see that, I forgot the, you have to have the various operators. And so we see that the amount of exergy that was picked up by the feed water was only 1720. And so I can do one last equation, and that is this. I'm going to say my eta 2 for the closed feed water heater is equal to, it's going to just be X out divided by X, I don't think it's X out divided by X in. And we see that should be 17 over 30. And so it becomes, let's see, what did I do wrong? I got an extra. Okay. X out, X in, X in, X out, divided by. Okay, let me try. Hold on a second. A to 2 C F is equal to X out, which is this one. And that's going so well. Let's see here. Okay, what I'm going to do here is I'm going to do a re-supercalculate, and I'm then going to go back and see if what happened when I messed up here. Okay, so both are there, and let's see at the bottom of this one. Okay, it did calculate it. So the second law efficiency of that component was 57%. And so we have the cycle panel gave us the two overall efficiencies, first and second law efficiency, and our own calculation said that for that that closed feed water heater, it had a defined second law efficiency of about 57%. 43% of the exergy was destroyed. Okay, with that is the solution of this particular problem. Thanks for coming in.